Thanks, Rachel. As Rachel mentioned earlier, today we're going to talk about understanding the importance of updated compressed air system controls through OEM expertise. This presentation will be centered around centrifugal compressor control systems. So let's move forward for a brief introduction. Then we're going to go through a historical overview of compressor controls, disadvantages and risk of legacy control systems, evolution of control system technology, advantages of modern control systems, the advantages of using OEM controls, and then we'll get to a little conclusion and some questions and answers. So a brief introduction on the evolution of compressed air system controls technology and the advantages of using new control system technology. So as demands for efficiency, reliability, safety, sustainability continue to grow, outdated system controls can become a hidden liability. So, draining energy, increasing operational cost, reducing overall performance. So this is where the expertise of original equipment manufacturers, or OEMs, play a critical role. So by leveraging the latest advancements in control technology and aligning them with the OEM insights, facilities can unlock significant improvements in system optimization, predictive maintenance, lifecycle management. So as we move forward with this presentation, we will explore why staying current with compressed air system controls is not just a technical upgrade, but a strategic investment, but best navigated with knowledge and support of the OEM professionals. So here's more of a historical overview of compressor controls. It's a little time phase, little timeline of where we started back in the early era and kind of where we are today. What you see here on the green is basically when it started. Red is when it was obsoleted, or it still might be around, but once again, it's very hard to update those components or those control systems. So back in the earlier, you had pneumatic controllers, analog electronic controls, manual operation, basic surge control. So with that, with the pneumatic controls, it used air pressure signals. These systems offered continuous feedback and adjustment, whereas the analog controls, they allowed more precise control, but they were still relatively slow, subject to drift. They had noise issues. The manual operation, the early centrifugal compressors, they used basic mechanical means. Operators manually adjusted valves, speeds are based on gauges and personal experience. And basic surge back then was poorly understood. Operators relied on conservative pressure ratios, and they had very wide safety margins. As we moved more into the mid-20th century, into the 60s and 70s, VME systems, Versa, module, Eurocards were developed. They were more computer board hardware. You had CPU boards, memory boards, you had serial interface boards, analog boards, digital boards, all with ribbon cables and big card cage, and a lot of those were used were more for an embedded system. They're still used today, more in the military and aerospace industry. They were considered very high reliability. Electro-pneumatic, still may see panels out there today. There are electrical signals to control pneumatic systems like valves and cylinders, enabling automation and precise control. Microprocessor, 8-bit systems. I know the old Elliott company had an EDC 8, EDC 16 microprocessor, along with Ingersoll Rand and different other companies that used like the Motorola 6809 microprocessor. They, examples, oh, go back, I'm sorry. Examples were like for 8-bit that we would know, 8-bit systems were like the Atari 800 or the Commodore 64. Back in the early 80s, Sega Genesis came out with a 16-bit gaming system. Just to kind of put it in perspective, what we had back in that time frame. Then during the late 20th century, or the 80s and 90s, that was commonly known as the digital revolution. You had DCS systems, PLCs, the introduction, distributed control systems, programmable logic controllers, that allowed for more complex, reliable, and automated control. You had industrial control systems, commonly plant system controllers, where you had integrated hardware and software configurations that used controlled automated industrial processes, which compressors, dryers, coolers, water skids, pumps, motor control systems, so many different things. You had improved surge controllers in the late 20th century. Basically, they were dynamic modeling and real-time monitoring, helped fine-tune anti-surge logic back then. You got into the microprocessor. They were upgraded from 8 and 16-bit to 32 to 64-bit systems, which supported multitasking, faster functions were performed, increased memory. Some common day examples were like PlayStation 1. The Nintendo 64 was a 32-bit system. PlayStation 2, 3, 4, and even today, PlayStation 5 used 64-bit system. When we moved into the 21st century, the 2000 plus era, you had advanced PLCs, Allen Bradley, Siemens, Modicon, GE. They represented a significant step beyond basic PLC functionality, incorporating features like advanced programming languages, complex algorithms, and enhanced communication capabilities for more efficient programming. There was advanced anti-surge control, real-time surge detection algorithms with high-speed actuation. So model-based control, where they used mathematical models of compressor dynamics for predictive and optimized control. Now in the present and future, in the 2020s plus, a lot of preventive predictive maintenance is moving into cloud-based SCADA systems. You have the IIoT, Industrial Internet of Technology, cybersecurity, AI optimization, and digital twins. So a lot of that today, you have remote monitoring and it controls the data and the analytics. And due to the increased digital connectivity, you have to secure the data better through the cybersecurity. So that's kind of where we're at today from a life cycle perspective. We're going to move forward now to the disadvantages and the risk of legacy control systems. So from this, you can see the disadvantages are obsolescence of parts and lack of OEM support, lack of technical support or updates, increased maintenance cost, operational risk and reliability issues. Some examples of obsolete parts, if you have analog panel instruments, like analog pressure, flow, temperature gauges were replaced with digital HMIs, SCADA interfaces, smart transmitters. You have mechanical linkages and cam-based control systems are obsolete now. Mechanical trip mechanisms, CAM-based surge control systems were replaced by software-based anti-surge algorithms and DCS or PLCs. Relay logic panels are now obsolete. They were hardwired electromechanical relay systems. They are now replaced by PLCs or DCS systems. A lot of the communication interfaces are now replaced. The RS-232, you'll still see RS-232, RS-485, RS-422 serial interface around, but a lot of that has been replaced with Ethernet, Modbus TCP or IP, or industrial protocols like Profinet, which is Siemens-based. Everyday examples that we still see today, you see from our standard landline phone to our smartphone, dial-up systems to fiber internet, your typewriter that you used to use to voice typing on your mobile phone today, beta to VHS to now streaming, from floppy disk to cloud storage today. All those are legacy or outdated systems for everyday common things that are now obsolete and hard to replace. Cybersecurity, like we mentioned earlier, poor integration with modern systems, loss of competitive edge. So to summarize all the disadvantages and risks, failing to consider part obsolescence and OEM support can lead to higher operational risk, cost, escalation, and reduced efficiency. So by proactively upgrading ensures businesses continuity, improved performance, and long-term sustainability. So the next couple slides, we're going to discuss the evolution. I'm just going to show you some pictures of the compressor control system and kind of where we're at today from where we started. So back in the 60s, I mentioned earlier, you have the pneumatic panel. The pneumatic panel was all pneumatic controls. And it was a lot to adjust these controls. And that was more in the mid 60s and 70s. Then we moved into the late 70s, the late 80s, you have electro-pneumatic panels. Even today, you may still see some of these out there that could be easily upgraded. And then you moved into the 1980s, where you had the VME systems, where there's a card cage in the panel with ribbon cables, in an LED screen, usually a 2-line 32 character LED screen. And then you move into the advanced microprocessor, which is current today, which you see in a lot of on centrifugal machines. You see a lot on recip and screw type compressors. That's more the transition to the digital PLC and DCS integration. They still exist today, and a good reason for that is for proprietary control systems, more of what they call a black box control system. PLC, current, the middle picture, is what is commonly used more as open architecture. You'll see a lot of customers want more of a PLC based system, whether it's Allen Bradley system, GE, Modicon. They may want Siemens. It depends on what they're looking for, what type of parts they may have in their inventory, in their plant. Usually predicates what they want, what type of system they want. And then you have advanced process control systems. You get into a lot of safety integration, redundant PLCs. You get into real-time analytics and machine learning, enhanced HMI and SCADA interfaces. So that's kind of where the future is headed and where we're going today. The next few slides are going to cover the advantages of modern control systems and the types of control that are found on centrifugal compressors. Different companies may have different names, but they typically all do the same thing, but some are better than others in regards to efficiency. So we'll explore the types of those systems. So some of the advantages of modern control systems: improve compressor operation through processing speeds, operator interface, you have the big HMIs now, performance and reliability, communication capabilities, serviceability, and OEM support. One of the big things today is if you connect and look at all your analytics, FS-Elliott does use a product called FS Connect, and it's a web-based remote monitoring 4G cellular connection, and which eliminates any need for connection so it protects the customer's firewall. It's a remote monitoring feature. And a lot of systems are using that today. So we're going to move into the control modes and how the control modes interact today and how they're efficient in today's compressor technology. So the first couple modes you see on the screen are base mode and suction throttle mode. Base mode is designed for systems that operate at full load within minimum load variation. So you can see the compressor surge curve in the top right corner. Suction throttle is designed for systems that operate at full or reduced load or without load variation. And that would be the one on the lower right. So the next slide will show an animation of suction throttle. So this slide here is going to animate suction throttle control. The X that you'll see, which is right here, is the compressor operating point. So as demand decreases, compressor will turn down, providing energy savings and eliminating wasted energy through blow-off. Another feature is auto unload, start and stop. These modes are great for users who have changes in demand and the desire to unload or stop compressors that are no longer needed to meet demand. Well, the auto start function can be used as a great feature to ensure that the standby compressors automatically start if demand increases. Another known control for efficiency is commonly called pressure band optimization. This offers constant system pressure control that helps compensate for downstream system losses from items such as dryers, piping, receivers. The control mode's PID loop will dynamically control the compressor discharge within the pressure band to ensure the constant pressure is maintained. Lower system pressure means higher compressor discharge pressure, while higher system pressure means the discharge pressure of additional turn down. So I'm going to animate how the PBO operation works, the pressure band optimization works. As you can see here, before I start the animation, you have the 110 PSI is your above design pressure band set point. Well, the 90 PSI is your below design pressure band set point. The control line would be established during commissioning by completing surge testing at each of the 3 pressure set points to ensure maximum turn down is across all the pressure bands. So you would do a discharge surge test, you would do a suction surge test to get your above and below set points. So as the compressor loads to its minimum operating point, as the downstream system pressure changes, the operating point will dynamically change through the PID controller within the pressure band. And it maintains that constant downstream system pressure, as you just saw. And the next mode is considered ambient compensation control. It's really designed for customers that experience daily or seasonal temperature changes. ACC runs an algorithm that will automatically adjust the compressor control line by monitoring the inlet air temperature. The control line will adjust to ensure maximum turn on and lower inlet air temperature conditions, helping to ensure maximum energy efficiency. During higher air temperature conditions, the control line will adjust to higher driver set point, ensuring the avoidance of unnecessary surge events. The X is the compressor operating point. The control line would be established also during commissioning. So the compressor loads to its minimum operating point and then loads to the required capacity and the compressor will throttle towards its minimum operating point, similar to the operation of suction throttle. But then as the inlet air temperature decreases, the control line will adjust, allowing for that additional turn down and energy savings. So this slide here is an example of the potential energy savings through the use of ACC. This is based upon the average monthly temperature in Pittsburgh at 54 degrees Fahrenheit. The estimated savings is approximately 5% per year and can be more or less depending on the regions and climate conditions. I'm going to start the animation here. The first line shown will be blue and outlines the energy usage when operating in suction throttle control throughout the year. Second line is the orange line and outlines the energy usage when operating in ACC throughout the year. And the third line is the gray line and highlights the energy savings between suction throttle and ACC. Gives you the cumulative energy savings cost, which is between $14,000 and $16,000. Another common control mode for a lot of compressor manufacturers is integrated compressor control, which works off of a peer-to-peer network where all the compressors are linked together. And ICC is an onboard built-in sequencing software that eliminates the need for standalone sequencing. So everything is controlled within the HMIs of the control panels where you can switch over. Any one of those could be a master controller. The system can network multiple compressors into a single system to ensure efficient and effective operation with multiple compressors within a single header. Some of the advantages of ICC include it provides overall system visibility to ensure that all critical operating data, pressures, temperatures, vibrations can be viewed on any of the networked compressors. Options for both lead, trim, and load sharing exist. And we're going to cover both the lead, trim, and load sharing here shortly. Some of the other options available in ICC are time leveling as well. So this animation will show the operating of each compressor in a lead trim style. And then the next part of the animation will show more of a load sharing. So I'll start the animation. So with the plant system running on a low system pressure, it starts up compressor 1. The system pressure is still low. The compressor will load to its maximum operating point within PBO that we discussed earlier. So it's running at 110 psig right now. With the system pressure still low, and it starts up number 2 and load to its minimum operating point. But noticing it was still low, it loaded to 110 psi. With the system still low, it started number 3. Demand was satisfied, but then it went low again. So it's loading number 3. So now that number 3 is able to meet the required system demand as the minimum load, now that all 3 compressors are running, you can see that as the demand increases, drawing down the system pressure, which results in the trim compressor, which is number 3. So what this animation doesn't show, though, is in a high system pressure situation, but if it did have a high system pressure situation, the third compressor, being the trim machine, would eventually blow off, and then it would shut that unit down. So now I'm going to demonstrate more of a load sharing. So with the demand satisfied, you'll see an example of how all compressors throttled to the same inlet position to equally share the required load. All inlet or guide vanes would position together at the same time and work together. So again, this animation really doesn't show a high system pressure situation, but if it did, all 3 compressors would throttle to their minimum operating points. And once all compressors are throttled to their minimum operating points, compressor number 3 or the trim machine, in this example, would be marked for blow off and eventually shut down. And as demand, as the plant needs more air, it would bring on those additional machines again. So some of the key points, why would we want to use integrated compressor control? It's great for a supervisory control system to maintain constant downstream pressure when operating several compressors in a single header. It's great for automatic starting and unloading and loading of multiple compressors due to changes in demand. Requirement or need to rotate a single or multiple standby compressor into operation without any operation interaction. Requirement or need to communicate critical operating data across multiple compressors. Why would the ICC be important? You have less operator interaction, maximum efficiency that maximizes the turndown and eliminates unnecessary blow-off. Rotation of standby compressors to ensure equal usage, especially if you're utilizing the time leveling feature. It minimizes the wear and tear of your compressors. Another common control mode is mass flow. So mass flow controls and measures the mass flow at discharge line to the plant system by adjusting the inlet valve. Maintains the user's targeted mass flow, ensures compressor operation efficiency, and avoidance of surge. So I'll animate this a little bit here. So this is really beneficial in different operating conditions where the ambient conditions such as temperature, pressure, relative humidity of the compressor location change, the necessary inlet valve throttle percentage to maintain the desired mass flow. Also, mass flow prevents driver overload and off-design conditions. The anti-surge control with mass flow works by adjusting the unloading control valve in response to the recorded pressure being delivered to the plant. The primary focus of anti-surge control is to maintain safe operation of the compressor by avoiding surging of the compressor, building excess back pressure at the compressor discharge to the point where there is a reversal of flow through the machine, and thus a potential for equipment damage. So I'll animate a little bit of mass flow and anti-surge control. The delivered pressure of the compressor, the anti-surge controls aid in maintaining this pressure, in addition to only avoiding surge, but in instances where the plant usage comes to a halt and the back pressure builds, the unloading valve opens to maintain the targeted pressure once the plant usage resumes. So mass flow and anti-surge working in combination. Well, just mass flow can be used. The benefits of these two in combination are maximized when both are used. So here's an example. Let's look at an example or a scenario in which the compressor is running in the winter, which also happens to be a slower time for plant operation. Let's say this is during the holiday season. Since the ambient temperature is colder than the normal operating conditions, you have less volumetric flow. So in that you have less flow, which is required to obtain the designed mass flow. So thus the current IGV setting exceeds the mass flow design. So at the same time, there is less air usage downstream of the compressors since operations have slowed down. I'm going to try to animate that situation. Here you have the mass flow control can be effectively throttled the IGV position in response to the different ambient conditions down to you'll see the dashed line there, which is the design set point. At this point, we will still exceed the targeted discharge pressure and are approaching the surge line. The anti-surge controls can then open the unloading control valve to reduce the compressor's discharge pressure to attain the new design point. I'll run through that one more time. Okay. The next slide, we're going to talk about the advantages of using OEM controls and understanding the importance of centrifugal expertise. So some of the key points and some of the key benefits are Energy Advisor, which works to provide the user with feedback related to the overall efficiency of their compressor operation. This will occur through an efficiency rating that is either good, marginal, or poor. The rating is typically displayed through a leaf icon. And like every system is different, they may not use a leaf, it just may be through text. But in this situation, if the rating is marginal or yellow, poor would be red. The Energy Advisor will periodically make recommendations to methods that can improve the overall operation. These recommendations can include suggestions to control modes or maybe enable your auto unload or start or stop features. So the Energy Advisor basically will tell you where your system is performing poorly and recommend what type of control mode you should control in. And it will also tell you your kilowatt usage based on the control mode that you're operating in. Maintenance notification system. I mentioned earlier that FS-Elliott offers remote monitoring, as do a lot of OEM equipment manufacturers. The maintenance notification system kind of works like some of the newer technology with cars, where it tells you when you need an oil change. But it tracks the usage of normal maintenance parts and advises with maintenance when you need it, when it's approaching. These types of notifications are provided as visual indications on the HMI now. They have alarm notifications, or a lot of DCS customers look at these through their Modbus protocol. The overall goal of this feature is to ensure the maximum compressor uptime. So in today's technology, maintenance notification system is big. Remote monitoring. Once again, another real big advantage today. This feature allows for web-based remote monitoring. The remote monitoring feature allows for complete machine monitoring by the end user or channel partner. It basically, every signal parameter is viewable and accessible through the HMI. You get alarm and trip notifications. You get operational Energy Advisor notifications. You get monthly operational and maintenance report highlighting a monthly summary of the compressor operation along with upcoming maintenance. So remote monitoring is now a big selling feature in today's technology. So what are some of the advantages and benefits of using centrifugal compressor control system OEM technology versus non-OEM? Optimized performance. Most non-OEM companies may offer some or a lot of these features, but do they provide some of these benefits? Optimized performance. What's a benefit on optimized performance? Well, OEM systems are specifically engineered to match the compressor's aerodynamic design and performance map. This guarantees higher efficiency and load control, surge avoidance, and energy management. Proven surge control logic. Benefit there, factory-tested surge algorithms, which are tuned to machine-specific dynamics. You have faster response times, reduce the risk of surge events and mechanical damage. Seamless integration. One of the big benefits are OEM controls are specifically designed to work with the equipment they're made for, ensuring seamless integration. They're pre-configured to interface with OEM hardware, sensors, actuators. They're easier, more reliable integration with DCS and SCADA systems. Predictive maintenance. And big benefit there is built-in diagnostic tools tuned to the known wear and failure modes of the machine, condition monitoring, vibration, bearings, temperatures, etc., specific to meet the customer requirements. Remote monitoring, access to OEM firmware, updates, technical support, spare parts. It's the nice benefit of remote monitoring with OEM equipment. It's specific to that machine. Warranty and lifecycle support. Big benefit there, using OME parts often maintains the equipment's warranty. You get access to factory level technical support, updates, diagnostics, which are probably unavailable with non-OEM options. Easier future upgrades and backward compatibility with older models. So OEM, they know how to evolve systems with minimum operational disruption. Enhanced reliability benefit there would be controls are tested and validated under the same conditions as the original equipment. They typically deliver better accuracy, stability, and response time, and speed and load regulation. Compliance and certification. Benefit there are they're designed to meet strict industry certifications and safety standards. There is reduced risk of integration issues, faster issue resolution due to in-depth knowledge of both mechanical and control systems, whereas like non-OEM alternatives might not meet the same certifications, leading into potential energy or reliability or issues down the road. System upgrade compatibility ensures access to updates and remote support, whereas non-OEM, you may not get that access for that machine. And lower total cost of ownership. Benefit there is downtime, repair frequency, energy inefficiencies. Overall, they provide a lower total cost of ownership over the life cycle of the machine. So in conclusion, the cost of inaction versus the value of modernizing your systems. Older systems are less efficient, leading to higher energy consumption and utility bills. Maintenance costs rise due to more frequent breakdowns and scarcity of spare parts. Legacy systems are prone to failures that result in unplanned downtime, production losses, and revenue impacts. Diagnosing and repairing outdated systems often takes longer, further compounding losses. Outdated controls also may not meet current safety or environmental regulations, increasing risk or accidents of non-compliance fines. And also an inability to integrate with modern plant-wide systems, limited processes, improvements. The value, though, behind all that, and the reason why you'd want to upgrade to modern systems today Modern controls optimize compressor operation, reducing energy use by 10 to 30% in many cases. There's advanced algorithms. They minimize wasteful loading and unloading cycles. New and retrofitted systems offer predictive maintenance, real-time diagnostics, fault-tolerant architectures. Reduced unscheduled downtime improves productivity and return on investment. There's seamless connectivity with plant-wide systems, enables centralized monitoring and control. Data insights allow for continuous improvement and benchmarking. New and retrofitted systems are built to comply with the latest industry standards and safety protocols. Scalability and software upgrade paths extend system life. Support for remote monitoring and digital transformation initiatives. So anything out there that's old, I recommend go out, do a system audit, and look for those systems that are outdated today and try to modernize the system and basically get them into an updated control system where you can show them the advantages of energy and efficiency and a lot of the value of modernization today. So that's the end of the presentation. I'll turn this over to Rachel and the questions and answers.